you've clicked on this video without watching the introduction first, I would recommend that you did watch it, as it will give you a perspective of what is going on. If you don't want to do that, then in a nutshell, I am describing an approach to understanding and interpreting quantum mechanics which does not start from quantum mechanics. A bit like the stranger asking for directions and being told, "I wouldn't start from here." In this video, I'm describing the first steps in developing a new theory called, for want of anything better, real wave quantum mechanics. The theory is not based on quantum mechanics, but we will develop it in such a way that it might show parallels to quantum mechanics. It's pretty obvious that quantum mechanics has something wavy about it. De Broglie started the ball rolling with matter waves, which then led on progressively to the wave equations of Schrodinger, Klein-Gordon and Dirac. So we will definitely start with waves. Also, we know that our waves must in some way link to something which will eventually have characteristics of mass. So, maybe it's sensible to start with a wave in a massive medium. Why not acoustic pressure waves, i.e. an ether? We're going to ignore any protestations about there being no ether. Even Einstein recognised in 1920 that the special theory of relativity does not compel us to deny ether. We may assume the existence of an ether, only we must give up ascribing a definite state of motion to it. So we're not worried about assuming an ether, but we will, of course, have to ensure that it eventually meets Einstein's conditions. And then we know that a key feature of fundamental particles is that they have angular momentum, both orbital, such as in an atom, and intrinsic within the individual particles. How can waves exhibit spin? Actually, spin in acoustic waves is a well-recognised thing. It arises when waves from different directions arrive at a particular point in space with a special phase relationship. Let's look at four plane waves arriving from, say, north, west, south and east, such that their phase differs by π/2 radians. Look at this animation of a cell with side 1 wavelength. In effect, a crest arrives from the north, followed by a quarter of a cycle later one from the west, then one from the south, then one from the east. What we are showing here is a density, because an acoustic wave consists of zones of compression and rarefaction. A zone of high density is chased around the point. But if the density is changing in this way, then there is some angular momentum, or spin, at this point. Plenty of experiments have been carried out to confirm the presence of this angular momentum. A disc placed at such a point is shown to be twisted when the speakers output waves of fixed frequency and the required phase relationship. So, for the moment, we can tick the box that acoustic waves can give rise to angular momentum or spin. What's more, they can, of course, describe spins in two different directions, because our choice of the north-east-south-west phase relationship was arbitrary. We could equally have chosen north-west-south-east. In the physical experiment, the disk would be twisted in the opposite direction. But isn't angular momentum supposed to be conserved? Well, if we pull out a bit from the animation, we see that we have been wrong to focus on a square of one wavelength. If we look at other points, we can interpret them as different spins. The spin at point B and the spin at point A are in opposite directions. Over the whole field, there are as many points spinning in one direction as there are in the other. Globally, spin angular momentum is conserved. So, spinny bits are possible features of acoustic waves, but they don't map onto quantum mechanics in any immediate manner. There is another fairly obvious question. Where are these waves coming from? Waves are the solution to a wave equation, which is normally linear. Technically, this means that if you have some waves which are individually solutions of a wave equation, you can add them up to get another solution. That's a bit mathematical, but if you want a more physical illustration, it is just that waves pass through each other. You can see this in this picture. It looks like a very complicated wave field if you get too close, but if you get far enough away, you can see that the waves are just passing unchanged through each other. However, it cannot be the case that at the most basic level, everything is linear. Schrodinger once quoted Einstein as saying that if everything were linear, nothing would influence nothing. It's a recognized dilemma, and we will choose to meet it head-on by making a fundamental postulate of real-wave quantum mechanics that the non-linearity arises here. We will postulate that part of the wave energy passing through a vortex is absorbed and re-emitted as an outgoing spiral wave. To make the postulate somewhat more concrete, we will say that there is always a fixed fraction that is absorbed and re-emitted, and we will call that fraction alpha. This is a very important postulate because if vortices can become sources, it may be possible to form interacting structures from them. This picture gives us some idea of this concept. Say that the vortices exist at the integer points on the square grid and have phase indicated by the direction of the rotating arrows. The spirals are the re-emitted waves. If you follow the spirals, you can see that they arrive at other points along the axes in phase, opening the door to structures which are to some extent self-supporting. However, where the wave direction is not along the axes, their arrival can be seen to be not in phase. We will need a way of sorting out all these different contributions, and we will address this in a later video. But there is still another problem. Say that a structure of interacting vortices was formed. Then it is inevitable that around the outside of the structure there will be waves leaving and taking energy with them. The structure would simply evaporate. There must be some balancing source of energy. Of course, the waves leaving a structure will in all likelihood sooner or later pass through another structure, albeit with greatly reduced amplitude, but roughly the same frequency up to perhaps a Doppler shift. But if we have a universe full of these particles, we can envisage that these lost waves will form an all-pervading stochastic wave field. We can resolve the lost energy problem by assuming that energy is regained from the stochastic wave field by a process of resonance. I have in mind that the stochastic nature of the wave field will generally cancel itself out during the course of one rotation of the vortex, except that waves which are in the correct phase for their direction will, for the brief period of their passage, enhance the amplitude of the nonlinear spiral wave. There is another issue which must be addressed. For hundreds of years, physics has lived with the concept of particles having electric charges. Generations of children have been taught, if nothing else in physics, that like charges repel and unlike charges attract. In fact, it is very difficult to turn off this picture of little things with a plus or minus written on them. But the structures we are putting together have no place for little pluses and minuses. They are just structures of waves interacting and drawing energy from the stochastic field. Where can we fit in the potential effects which are so obviously a key part of regular quantum mechanics? The solution tried for real wave quantum mechanics is that a potential represents a modification in the local stochastic field which alters the resonant gain term, either increasing it or reducing it. In this way, we might expect that a static potential field would control the shape of an interacting structure without recourse to little pluses and minuses. So in summary, we hope to find a stable structure of interacting vortices containing spin angular momentum whose overall form is controlled by potentials whose effect is to modify the local resonant gains from the all-pervasive stochastic wave field. Looking at this process in a more general way, the important thing to bear in mind is that all postulates are only as good as the results they lead to. If these postulates lead to nonsense results, so be it, back to the drawing board. But of course they don't, or I wouldn't be making this video. That's it. Crazy, isn't it? How can that resemble quantum mechanics? We will look at that in the next video, and we'll see that it is quite easy to implement these postulates to try things out. Meanwhile, here's a picture of a three-dimensional structure calculated using real-wave quantum mechanics based on a simple harmonic oscillator potential.